Welcome to the tutorial part, sheet 4, 3-phase induction machines. Here we are going to solve basic problems related to 3-phase induction motor. To start with, we are having a 3-phase 20 HP 208 60 Hz 6-pole Y connected induction motor which delivering 15 kilowatt at a slip of 5%. At a slip of 5%. We need to evaluate the synchronous speed, rotor speed. Synchronous speed is the speed of the alternating flux, rotor speed is the speed of the motor, and rotor frequency of the rotor current. These things we need to evaluate for the first problem. If we move on to the solution, let us write the given data. Slip has been given as 5%, so S is equal to 5%, which is equal to 5 divided by 100 is equal to 0.05. Number of poles P is equal to 6, F is equal to 60 Hz. Synchronous speed Ns is equal to 120 F by synchronous speed. Ns is equal to 120 F by P, which is equal to 120 into 60 by 6. We can write it as 1200 RPM. Rotor speed is Nr is equal to 1 minus S into Ns. Slip has been given as 0.05 value or 5% into 1200. When you evaluate this rotor speed, we will get it as 1440. What do you mean by rotor speed? The speed of the rotor or the speed of the motor, which is slightly less than the 1200 RPM. This is the synchronous speed, which is the speed of the alternating flux. We consider this as speed of the alternating flux, whereas this rotor speed 1140 is the speed of the rotor or speed of the motor, which should be slightly less than the synchronous speed for running this machine as an induction motor. Frequency of the rotor current, it is of the factor called S with the fundamental frequency. S is the slip, F is the fundamental frequency. S into F we will get it as frequency of the rotor current. So which S value is 0.05 and F is 60, which is equal to 3 Hz. This forms your first question. Very simple problems. Coming to the second question, we are having a 3-phase 460 volts 100 HP 60 Hz 4-pole induction machine. This is the supply voltage, power rating, frequency, number of poles. IM induction machine, which is delivering rated power output at a slip of 0.05. 0.05 is the S value. We need to evaluate synchronous speed, motor speed. Here we said rotor speed, and here I am saying motor speed. Both are same. Motor speed is considered as the speed of the rotor, frequency of the rotor current, and slip speed, and also slip speed. What do you mean by slip speed? Slip speed is the difference between the synchronous speed and the rotor speed, or the synchronous speed and the motor speed. We will start one by one. To start with, the given data, S is equal to 0.05, P is equal to 4, frequency is equal to 60 Hz, and synchronous speed Ns is equal to 120 F by P. Synchronous speed and 120 F by P. Substitute the value of F 60 Hz, number of poles given 4. When you evaluate, you will get it as a 1800 RPM, and Nr is equal to 1 minus S into Ns, which is equal to 1 minus 0.05. Substitute the value of, now we are calculating the rotor speed. Rotor speed is equal to Ns minus S into Ns. The speed less than the synchronous speed. So 1 minus 0.05 into 1800, you will get it as 1710 RPM. So rotor frequency is equal to SF is equal to 0.05 into 60 Hz. We will get it as 3 Hz. Fr is equal to SF is equal to 0.05 into 60, 3 Hz. slip. N slip is equal to S into Ns. S value is 0.05, Ns is equal to 1800, which is equal to 90 rpm. This is one form, or you can simply differentiate, take the difference of 1800 minus 1710. You will get the same thing, Ns minus Nr. Either you can go for slip speed S into Ns, or you can opt for Ns minus Nr. You will get the same value. We call this as slip speed. This is the difference between the synchronous speed and the motor or rotor speed. Coming to the third problem, we need to determine the number of poles, slip and frequency of the rotor at rated load for a 3-phase induction machine. We are having a 220 volts Y connected 60 Hz 588 rpm. This is one machine. Another machine is 120 volts Y connected 600 Hz and 873 rpm. For these machines we need to calculate the number of poles, P, S, and frequency of the rotor current. Frequency of the rotor current. Previously he has given the value of P, frequency, and he has given the value of slip. Now, and we have evaluated synchronous speed, rotor frequency, and slip speeds, related mostly related to the speed values. Whereas here he has given the speed value, frequency value. Now we need to evaluate number of poles, slip value, and the frequency of the rotor current. This value we need to evaluate. To start with, go to the solution. Question number 3. 220 volts 5 Y connected 60 Hz rpm. This is the rotor speed, but this is not the synchronous speed. We will assume that we know that rotor speed is almost near to synchronous speed. Check it here. This is rotor speed almost nearer to 1800 and 1710. It means slightly less than this. And here also rotor speed, synchronous speed is 1200, and here we got 1140. It means it is nearer to this. So in problem number 3 we will assume that the rotor speed is almost nearing to the synchronous speed. It is almost equal to synchronous speed. We will say it as 588. We know synchronous speed Ns is equal to 120 F by P, 120 into 60 by P, which is equal to 588. We are assuming this. We are assuming that this value is the synchronous speed, but it is not. Just for evaluation of the Ns value, we will assume that 120 into F by P is equal to the rotor speed. We will get it as P is equal to 120 into 60 by 588. We will get it as 12.244. But if you check, there is no pole with this number. It should be nearer to this. It should be nearer to it some numerical value, some an integer, either 1 or either 2 or 4 or 6, or it should be in even numbers. Poles exist in even numbers. So the nearest even number to this number is the 12. So we will say that number of poles P is equal to 120. Now taking this into consideration, synchronous speed Ns is equal to 120 into 60 by 12. We will get it as 600 rpm. See, 600 rpm. Ns is equal to 600 rpm and Nr is equal to 588. Now we will calculate the slip. S is equal to Ns minus Nr by Ns, which is equal to 600 from here minus 588, which is given in the problem, divided by 600. Ns minus Nr by Ns, which is equal to 0.02. This is your slip value. Now frequency, rotor frequency can be evaluated. Fr is equal to Sf. We got Sf here, and frequency is given as 60 Hz. 0.02 into 60, you will get it as 1.2 Hz. 1.2 Hz. This is first part of the problem number 3. Coming to the second part, we are having 120 volts Y connected 600 Hz and 873 pm. Is it 600 Hz? Yes, it is 600 Hz. No problem. We will assume that when we don't know the synchronous speed, we will assume that the rotor speed is the synchronous speed. So Ns is equal to 873, P is equal to 120 F by Ns, which is equal to 120 F value 600 divided by 873. We will get 82.474, but it should be a nearest even number. The nearest even number 83. If you are going for 83, it is odd and it does not exist. So the nearest even number is 82. So P is equal to 82. 82. So we can write it as P is equal to evaluate the synchronous speed, Ns is equal to 120 F by P. In place of P, we will substitute 82. F is equal to 600 Hz, already given. 120 into 600 Hz divided by 82, we'll get it as 878 RPM. Synchronous speed Ns is equal to 878 RPM. Now slip can be evaluated as Ns minus Nr by Ns. Ns value we got 878, Nr value is given 873 divided by 878, you will get it as 5 divided by 873, which is equal to 0.00569. This is the slip value. If you want to calculate in percentage, divided by 100, you will get 0.5 percentage. If you want to evaluate the slip value in percentage, divided by 100, you will get 0.002. This is just slip in numerical value, and here slip is also in numerical value. So Fr is equal to SF. Fr is equal to Fsf, rotor frequency. Substitute the value of S, which is evaluated here. Substitute the value of F, frequency 600 Hz given in the problem. We will get it as 3.414 Hz. This completes your problem number 3. Coming to the problem number 4, the full load speed of a 25 Hz 3-phase induction motor is 720 RPM, whereas its no load speed is 745 RPM. Find the slip of the machine at full load. This is the full load speed. It means when the machine is loaded completely to the maximum capacity, the speed of the motor is 720 RPM. And its no load speed, and it means no load is connected. Under that condition, this is the speed of the machine. We need to evaluate the slip of the machine. We consider that no load speed as the synchronous speed. No load speed is almost equal to, when no load is connected, the rotor will be almost nearer to the speed of the machine, speed of the alternating flux. So NL or NS both are same. So simply slip is equal to NS minus NR by R. No load speed minus NR by NR. This is also one new formula, which is equal to NR value 745, NS value 745, NR value rotor speed under load condition 720 divided by 745. You will get it as 0.0335. This is the slip of the machine. Coming to the fifth problem, we are having a 3-phase 10 HP squirrel cage induction motor, which is wound for 6 poles. When the motor is connected to 230 volts 50 Hz supply at a full load, operate at 4% slip. 3-phase machine, power rating P is equal to 6, supply voltage is 230 volts, 50 Hz frequency, S value is 4 by 100, 4% means 4 by 100. We need to evaluate the full load speed. Full load speed is nothing but rotor speed. For this load, we need to evaluate the full load speed. So NR is equal to rotor speed. We need to evaluate the rotor speed. The termination is changed, but the formula is same. NR is equal to NR full load is equal to NS into 1 minus S. Why this slip is this value? It means at this load, this is the slip value. So NS into 1 minus 5. NS value is synchronous speed is 1000. How do we got that 1000 synchronous speed? From here, Ns is equal to 120 F by P. 120 into 50 divided by 6, we will get it as 1000 RPM. We got synchronous speed value. Synchronous speed into rotor full load value is equal to 1 minus the slip value. Slip value is 4%, means 4 by 100 is 0.04. 4 divided by 100 is 0.04. 1000 into 1 minus 0.04, you will get it as 960 RPM. So the next parameter is torque. We need to evaluate the full load torque. Torque is equal to P by omega. Angular speed, power output. Power output is equal to, he has given us 10 HP. 10 HP is equal to, we can write it in watts, 10 into 746, converting HP into watts. Converting HP into watts means we need to multiply HP value into 746. 10 HP into 746, we will get it as watts, divided by omega is 2 pi n by 60. N value, synchronous speed, rotor speed, is given as 960. 2 pi into 960 divided by 60, you will get it as 74.2 Newton meters. The next parameter that has to be evaluated is rotor frequency, frequency of the rotor current. Frequency of the rotor current, as usual, Fr is equal to S into F. S value is given as 4%. 0.044% can be written as 4 by 100. We'll get it as 0.04 into 50, which is equal to 2 Hertz. Coming to the D, Ns is equal to speed of the stator MMF. Speed of the stator MMF is equal to synchronous speed, as we did in the previous problem. See, no load synchronous speed or the no load speed 745 rpm. This is the synchronous speed. This synchronous speed is also equal to the speed of the stator MMF. Just the termination is changed. Speed of the rotation of the stator MMF, nothing but speed of the rotational magnetic fields. Speed of the rotational magnetic field, it is the same as that of the synchronous speed, 1000 rpm. Coming to the problem number 6, we are having a 10 HP 4 pole 25 Hertz 3-phase wound rotor induction motor is taking 9100 watt from the line. Core loss is 290 watts, stator copper loss is 568 watts, rotor copper loss is 445 watts. These are all losses, and also friction and windage losses are also there. See, transformers and induction machine, both are same, almost same. The only addition is, in transformer we don't have this friction and windage losses. We will have core loss, we have stator copper loss, primary winding loss, core loss, iron loss, primary winding loss, secondary winding loss in the transformer, rotor copper loss, secondary copper loss, primary copper loss, secondary copper loss. Friction and windage losses are mechanical losses. Mechanical losses in transformers are 0. In addition to the transformer loss, we have friction and windage losses, mechanical losses in the machine, in the induction machine. Almost the same, both works in the same principle. So it means both have the same principle of working, except the mechanical part, rotational part. We need to calculate the power transfer across the air gap. It means from the stator to the rotor, what is the power available, power transfer, what is the power transfer from the stator to the rotor part. Nothing more, we can say it as power transfer from the primary to the secondary. Mechanical power in the watt developed by the rotor, mechanical power watt developed by the rotor. It means including mechanical losses. So mechanical power output, it means after removing the mechanical losses, what is the power available. Then we need to evaluate the efficiency, slip, torque at the shaft running at 710 rpm. Torque of the shaft at the shaft running at 710 rpm. To start with, one by one we will deal it. Let us write the given data. Power input to the motor is 910 watts. Power input to the motor, it is taken as, see, motor is taking 910 watts from the line. This is the P value. P value is 910 watts. Power in the air gap is, where is the power input is given? Power input is given to the stator. It means this power is given as an input to the stator. Power in the air gap will be what? The power, a part of the power will be consumed in the stator. So we are removing that loss. That loss in the problem is given as, stator copper loss is given as 568 watts. Stator copper loss is given as 568. So we need to eliminate all the losses which are present in the stator. What else loss we have? We have core loss and also stator copper loss. Core loss means loss in the stator. P input minus P loss in the stator. P loss in the stator stator loss is P loss in the stator core, P loss in the stator winding. P loss in the stator core is 290, P loss in the stator winding is 568. So completely on evaluation you will get 8242 watts. Power in the air gap is power input to the stator minus loss in the stator. Loss in the stator is because of two reasons. One is supplying stator core loss, supplying stator winding loss. Stator core loss is 290, stator winding loss is 568. So total you will get it as 8242 watts. Coming to the mechanical power developed by the rotor, P mechanical. So rotor input minus rotor copper loss, rotor input PAG minus rotor copper loss is P rotor copper loss is 445. So 8242 PAG 8242 minus 445, you will get it as 7797. What is the power input to the rotor? The power which is available in the air gap. There is a gap, some air gap between the stator and the rotor. That power is this value, and this is the power which is given input to the rotor winding, to the rotor. And the power developed by the rotor is rotor input minus losses in the rotor. Losses in the rotor are rotor copper loss. So PAG minus rotor copper loss. Then PAG is equal to 8242 minus 445. 8242 minus 445. 82. Power air gap is here. Rotor copper loss, it is given in the problem. 445 watts. 445 watts. Or simply you can see it in the question also. You will get it as 7797 watts. So P mechanical output is equal to rotor output is equal to P mechanical develop minus P mechanical loss. Rotor output is equal to P mechanical develop minus P mechanical loss. P mechanical develop is equal to 7797 minus P mechanical loss is equal to 100, 7697. This is the rotor output. This is the power developed in the rotor, and then this rotor is rotated on a shaft. Because of that shaft we are having mechanical loss, and if we eliminate that, the remaining power is available for the usage, that is which we call it as an power output, and 7697. So power efficiency of the machine will be power output minus input. Output is this much and 7697, and input value is given in the problem 9100. After evaluation you will get it as 84.58%. 84.58%. The next parameter that we need to evaluate is slip. Slip is rotor copper loss divided by the rotor input. Rotor copper loss, this is also one formula for this slip value. Rotor copper loss, it is given in the problem. Rotor copper loss 445. Rotor copper loss is 445, and then we need to divide this rotor copper loss to the rotor input. What is the rotor input? Rotor input is the power in the air gap. Power in the air gap is evaluated here, 8242. Power in the air gap. So we will get it as rotor copper loss divided by the rotor input. You will get it as slip 0.05399. This is the slip value. Torque output will be P out by omega. Power output is 7697, which is evaluated here, divided by omega is 2 pi nt by 60. N value is 710. How we got N? Is it given in the question? 710. Shaft running at 710 rpm. Running at 710 rpm. It is given in the question. Running at 710 rpm. So 2 pi n by 60. You will get it as 103.5 Newton meters. With this, we have finished the problems related to the induction machine. We have covered problems related to the speed of the rotor, speed of the alternating flux, rotor frequency, slip, evaluation of the synchronous speed, evaluation of the number of poles, evaluation of the full load speed, full load torque, rotor current, and speed of the rotation of the stator MMF. It is nothing but synchronous speed, we can say, and also the efficiency related problems where different power flow this problem is related to the power flow from input of the input power input to the stator, air gap power, losses in the stator, power input to the rotor, losses in the rotor, and then power output, along with that efficiency of the machine. These things we have evaluated in today's session. With this we conclude this session. If you are having any doubts, we can discuss it.